Hello again. This is Math 1428, Remote Delivery for April 20th, 2020, Part 2. And here we're covering Section 6.2 content. And please use controls like this to perfect your understanding while you're watching the video. The objectives are we're going to solve systems of linear equations in 3 variables now, not just 2. We're going to use systems of 3 equations to solve applied problems. Of course, those are word problems, and we're going to model a situation using a quadratic function. A linear equation in 3 variables is an equation equivalent to one of the form ax plus by plus cz equal d. The a, b's, and c's are constants, real numbers, and the d is also a real number, and x, y, and z are variables. A solution to a system of 3 equations in 3 variables is an ordered triple that makes all 3 equations true. So this is going to be x, y, and z. So this triple, 2 minus 1, 0, is a solution to this, and you can system, because you can verify this by substituting 2 for x, minus 1 for y, and 0 for z in each of the 3 equations. We're going to use a technique that's called Gaussian elimination. It's named after someone named Gauss. And our goal is to transform the original set of 3 equations and 3 unknowns into an equivalence system, one with the same solution set, that is of this form. ax plus by plus cz equal d, ey plus fz equal g, and hz equal k. Now you see, this is a simple equation because we just divide both sides by h and we solve for z. Then we can take that value for z and substitute in this equation. That becomes a number, and then we can solve for y, and then we substitute the values for z and y into the first equation, and we solve for x. So that enables us to solve the third equation for z, back substitute to find y, and then x. And we use each of the following operations are used to transform the original system to an equivalent one of the desired forms. We can interchange any 2 equations. Of course, that wouldn't change anything. We can multiply all the way through both sides by a non-zero constant of any of the equations. And we can add multiples of one equation to another and replace that with the new equation that we get by doing so, and that is still an equivalent system. Okay, let's wade into an example then. So here we want to solve the following system. These equations are numbered 1, 2, and 3. So what we're going to do is we're going to look at equations 1 and 2, and we're going to eliminate the x. And we can do that by multiplying all the way through in the top one by minus 4. Let's do that. Here we're multiplying by minus 4. Then we're adding and we're getting this. Now we only have 2 equations and we have 1 equation and 2 unknowns. But then we're going to do the same thing with equation 1 and equation 3. Here we're multiplying all the way through equation 1 by minus 3. We add it, and now we've eliminated, and now we have 2 equations, this one and this one, and 2 unknowns, y and z. So we have this. Now what we're going to do is we're going to use the techniques of section 6.1 to solve this equation. So let's do that. So we come up here, and what we find out is we eliminate the y. We have 35z equals 70. So you see, now here are the 3 equations and 3 unknowns. But this is going to tell me, when I solve equation that I'm calling 7, that z is equal to 2. And then if we take 2 and substitute it into this next equation up there, the one we called 4, we get this. That tells me this y is minus 1. And finally, we can back substitute minus 1 for y and 2 for z in equation 1 and solve for x. Here we do it, and we get x is equal to 3. And you could check this if you wanted to. I encourage you to test your understanding by trying this problem. Let's look at another example. So now we're going to be solving this system. Now, the thing that happens when we start trying to do the same technique here, what we will get is these are the 2 equations and 2 unknowns. But we note that Equation 4 is just minus 1 times both sides of equation 5. So when we add those together and try to solve it, we get 0 equals 0. Now, 0 equals 0 tells us that those three equations are dependent. This means that the original system of three equations is equivalent to a system of two equations. One way to see this is to note that 4 times the first equation minus equation 2 is equation 3. Okay, so that means that what we have is really just two equations, these two. So what we can do is we can eliminate the x from these. So if we eliminate the x from this, we get this expression. And that says that y is equal to, and we get y in terms of z. Now we can back substitute this into the original equation to find out that x is also this in terms of z. So you see the solutions to the system of equations are ortho triples of the form. This is what x is in terms of z. This is what y is in terms of z, and z is an arbitrary parameter. Z can be any real number. So, for example, if we chose z to be equal to 0, we would get this as one of the points. If we chose z to be equal to minus 1, we have this. But the solution to this system is going to be this. Any set of points that satisfy this for any value of z is a solution. Perfect your understanding by trying this exercise. Now notice if it would be possible for us to get a false equation such as 0 equal minus 5 somewhere along the line, and that would mean that the original system is inconsistent. There is no solution. Now, although systems of three linear equations in three variables are not appropriate for graphical solutions on your calculator, we can talk about what happens. You see, each of these equations represents a plane or an infinite piece of paper, if you want to think about that. So they could have three pieces of paper intersecting in one point, or not intersecting at all. No point is common to all of them. Or they could all be parallel this way, or they could intersect having infinitely many solutions like the one we just did, where it's along a line like that in three-dimensional space. Or in fact, we could have infinitely many solutions where all of these are identical. It's really a pretty complicated situation. Let's do a word problem now. So we have Amara inherited $15,000 and invested part of it in a money market account, part of it in mutual bonds, and part of it in a mutual fund. After 1 year, she got this much total interest from the three investments, and these are what they paid. The money market paid 4% annually, the bonds paid 5% annually, and the mutual funds paid 6% annually. There's an additional constraint. There was $2,000 more invested in the mutual fund than in the bonds. So find the money Maura invested in each category. Okay, so we're going to let X, Y, and Z represent the amounts invested in the money market, bonds, and mutual funds respectively. Then the amount of income produced annually by each investment is given by, we multiply by the percentage as a real number, not as a percentage, and so we get 0.04x, 0.05y, and 0.06z. So now we translate the terms of the problem into equations. Well, she had a total of $15,000, so x plus y plus z had to be $15,000. Since the total amount of interest she earned was $730, we have a second equation, which is this one. This is the income from the first investment, second investment, and the third investment adds up to $730. And the other thing says the amount invested in the mutual fund, Z, was, which corresponds to is, and it corresponds to the equal sign, 2,000 more than, we add a plus sign, the amount invested in bonds. So you see I do have three equations and three unknowns. So here are the three equations in, three unknowns, and we can solve these exactly as we did the other problems. I encourage you to perfect your understanding by doing this, but you'll get 7,000, 3,000, and 5,000. So those are the answers, and we describe it here, what she invested where, and I encourage you to test your understanding further by trying this exercise. Last, we recall that when we model a situation with linear equations, we need to know 2 points. And for a quadratic equation where we have y is equal to f of x is equal to ax squared plus bx plus c, we need 3 data points to determine what a, b, and c are. So here's a problem. We have the following data about the number of civil cases pending in U.S. federal courts for 3 years, and what we're supposed to do is use this data to find a quadratic function that gives the number of pending cases as a function of number of years after 2009, so we're letting that to be 0. We then use this to estimate the number of cases pending in 2014, and that means we're going to let x be 5. Okay, so what we're going to do is we're going to take these data points 0, 311, 353, 2, 267,495, and 4, 3,469. So when we plug those points in to the quadratic equation that we're seeking to model, that is the number of cases in year x is ax squared plus bx plus c. X is the variable, a, b, and c are constants. You see, we'll get this for 0. We'll get this for putting 2 in, and we'll get this for putting 4 in, and that gives us 3 equations and 3 unknowns. Now this is solved readily because we can take this value, substitute it in here, and then we have 2 equations and 2 unknowns. But if we solve it, we get this as our coefficients. A is going to be 9604, B is going to be minus 41,137, and C is going to be 311, 353. So this is the model that we have. So then, to answer the final part of the question, we're going to substitute 5 in, and we'll get this as our estimate for the civil cases pending in the U.S. courts in 2014. Now, students should note that you could have used quadratic regression for those 3 points, and you have to use quadratic regression if you have more than 3 data points. You can perfect your understanding by trying this problem. But now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of others. See you in